Yes, yes,
Okay,
you
great.
are.
So I want to model this process, which I've just shown you in the videos. So here are a few facts. We have, so 93% of astrocytomas have these tumor microtubes, which is a lot, which is essentially all of them, essentially. The tips extend and also retract. We saw this. The tumor microtubes follow directional features of the brain tissue, like blood vessels and nerve fibers. The nuclei divide separately and move along the tumor microtubes, and then they settle and form new glioma cells. And then a network forms which communicates via calcium waves. So we want to model all this, except the last one, we didn't do that, but maybe this comes later. Okay. So here's the modeling. And with Nadia Loy, Kevin Painter, and Ryan Thiessen, we discussed this for years. I think we took 3 years to come up with the model, just because it was so difficult to decide what do we want to model, which is which, etc. What are the terms we need? And so we came down to this. So we have a variable p for the tips. So the tips are the little red tips here. We have m for the tumor microtubes, right? These are the connecting lines. We have B for the bulk tumor cells, which are here. These are the Bs. These are the Ms. The tips are the Ts. Then we have moving nuclei. So here is a moving nucleus, or here. So this is the N. And then the resting nuclei are those which develop into bulk tumor cells. So we thought that we need these 5 components for a model to describe this process. All right, so now look at these terms. Before I show you equations, just look at these terms here. Because 3 of them depend on a velocity v, right? Here's a v, and here's a v, and here's a v, whereas the other 2 do not have a velocity. So v is a direction, and the tips, they move in a direction. So we need to use the direction as a parameter inside this density direction. And the microtubes as well, right? The microtubes grow in a certain direction, so it's also important to know what this direction is. And the moving nuclei, they move along the microtubes. So again, this is directed movement. And what is better to describe directed movement than transport equations? So the equations for P and M and N will be based on the idea of a transport equation. Okay, so I show you what that is. Here's the tumor microtube tips equation. And so this bit here describes the transport. And maybe let me first talk about the other terms, okay? The other terms are easier. So we have just a decay term with the rate alpha. Anastomosis means that a microtube hits a cancer cell, B. So if a tip comes to a cell B, then they make a connection and they are lost as a tip. And then the microtube tips are produced by the bulk cells where we use the logistic growth term for the production. Okay. So let's come back to the transport. So the transport term here describes cells moving in direction v with a speed sp, and we can measure the speed from the videos, and v is the direction. So this is the directed movement, characteristic derivative. And then the change of direction is described by a turning operator L. And I show you L in a second on a separate slide. But so this is an integral operator. So this entire thing becomes an integral PDE. So we have an integral term on the left, on the right, we have a differential term on the left. So it's an integral PDE, which looks as ugly as it is. So this may be maybe a little bit difficult. So let me just outline this transport term just a little bit more. So then I write it down. So time derivative plus SP V times gradient P. And so then the turning operator is the turning rate minus mu pli plus mu integral over velocity space T of VV prime P of Tx V prime dV prime. And then mu is called the turning rate. So this is how often does a microtube change direction when it grows. And we see in the videos, it does not change very often at all. So the turning rate is typically rather small in this case. And the T of VV prime is the turning kernel. So it's the probability density of switching from V prime to V. So this describes how they change direction, if they change direction. Okay. Now, in this talk, I do not want to go into details of transport equations. So there's an entire theory, and there are papers, and some are from me, how to deal with them, and what can be done, and existence, and all that stuff. I skip those details for the purpose of this talk, and rather focus on the biology a little bit more. Okay. But this purple thing here is the transport term, which I underlined just previously. All right. So next equation. So here is the microtubes M, and the microtubes are produced by the tips, which is this term, and then they can mature into bulk cells if a nucleus comes and settles. Okay, so N are the nuclei, and they form then bulk cells. So that equation is super easy, actually. Then the tumor bulk can grow. So we use a logistic term. We have a direct growth with the rate rho, and then we have this microtube-driven growth from the resting cells, which we call gamma R, and then they grow into bulk cells. So this is, again, a simple equation. The moving nuclei is not a simple equation. So we again have a transport part here, where the turning kernel now uses the microtube directional distribution inside this integral term. So n bar, I didn't say what n bar is. So n bar is the integral of n tx v dv. So it's the integral over all velocity, and still depends on time and space. Okay, then we have a logistic growth term again. This is how the nuclei divide, and then they rest and become resting nuclei with this rate kappa. So one more equation for the resting nuclei are, they're produced by the moving nuclei through this term, and then they become bulk cells through this term here. Okay, so do you have a complete picture of all the equations? Well, here it is. So here we have 5 equations. 2 of them are transport equations, 3 of them are ODEs, and everything is coupled, and this looks like a complicated beast. So then the question is, what do we do with this complicated beast? So this is a little bit too much for us, maybe for applications or also for analysis. This is actually rather hard. Before I look, though, into simplifications, maybe, I first estimate the parameters. So there's a whole bunch of parameters, alpha, beta, gamma, delta, etc. We can get them all from the videos. These videos are so detailed. We can see how quickly cells move. We can see how quickly the microtubes grow. We can see how often they change direction and all that stuff. So we get a very good handle on all these model parameters, which is really nice. Okay, back to this monster thing. So if I give this to Jack Yong Kim, so what would he do? He would probably throw away all spatial terms and first look at the ODE situation, right?
Nowadays, I'm doing PD.
So that's the kinetic part. So what I would like to do first is throw away all these ugly spatial terms, this one as well, and look at the dynamics of the resulting ODE, if this makes any sense in the context of these microtubes. So I do this, I think, here. Yeah, here it is. And then this is just a 5-dimensional ODE. And the worst terms are quadratic, lots of logistic terms, mass action terms, logistic terms. So this is stuff we can handle. Nobody should be afraid of this. So we can look for steady states and for the stability, run some simulations. So let's do that. So we get a continuum of disease-free steady states where the cancer, this is the cancer, is 0. And then we have a continuum of disease steady states where the cancer is at carrying capacity. These are the steady states we have. The M's are coefficients, so we can have some microtubes in both cases. Okay, the simulation is interesting. So look at this. Here we simulate the 5 compartments over time. Here's time in hours. And so what you should see, and I think you see it very clearly, is at the beginning here, the first thing which shows up is red, and then it is followed by the blue very quickly, right? And red is the tips, and blue are the microtubes. So the first thing happens is the build-up of tips and microtubes, and then this is followed later by the bulk, which is black, and then also by the nuclei, which is these colors tan and violet, which then build up the bulk. So this is clearly microtube dominated, right? The microtube set the stage, and then everything else follows. So just to try it out, we simulate a little treatment right here at day 3000 or at time 3500. We just take away all the cancer cells. We take away all the black. We set black to 0, but everything else we keep. So we keep the microtubes in the system, and then you see the cancer comes back very, very quickly, even quicker than it came before. And this is already, I think, one of the reasons why treating brain tumors is so difficult, because if you leave the microtubes in the brain, then from there, you can get regrowth of the tumor very, very quickly. Okay. So then back to the spatial case. Now, Nadia Loy, she wrote a numerical scheme for the 5 equations which I've shown at the beginning, which has the transport equations and all this. So she wrote a numerical code for this. And she found these wonderful invasion fronts. You can clearly see a constant invasion speed. And importantly, if you look close here, I think I can blow it up, that the invasion front, again, is dominated by red and blue, so the tips and the microtubes, and then followed by the black, which is the cancer cells. Okay. So, still, the model is too complicated. And now I would like to advertise model reductions, which are methods to make the model simpler. Now, where's my pen? Give me my pen. Okay. And here's a schematic of the model reductions I'd like to discuss just a little bit. So we are here. This is the full model, the black one. And here are a whole bunch of assumptions, A1, A2, A3, A4, until we come to maybe a simpler equation here at the bottom. And this looks completely scary, but there's a good reason to do this, because this model down here is the Swanson model. It's a PI model. Okay, and then this model here, this one here, is the go or grow model. And this model here, this one is the anisotropic model. So what I plan to do is to find scalings or quasi-steady state assumptions or something, so that I get actually the 3 models I started with as special cases: the PI model, the go or grow model, and the anisotropic model. If everything works out, they will show up here as special cases in this schematic. So let's go through this, just maybe not too quick, but also not in too much detail. So first of all, I assume that the quasi-steady state, so that the resting nuclei are in quasi-equilibrium. And what else? The microtubes are in quasi-equilibrium, following the direction of the tips. So quasi-equilibrium means 2 things. It means the corresponding reactions are quick, are fast, so that the time derivative in our differential equations can be set to be equal to 0. So meaning in our equations, we set these time derivatives here to be equal to 0, okay? And you see all equation, they have like a kappa and m term, and here it's the integrated one. But you can immediately see that this can be simplified. Here you can solve kappa and m is sigma p, you put it there, you put it there. You can solve for r or for p or whatever you want, okay? So this is very much handlebar with analysis. And what we keep is an equation for p and for b. And this is on the next slide. This is right here. So this is what you keep for the tips and for the bulk, where we still have a transport equation for the tips. So let's scale the transport equation. And there's something which is called diffusion limit or parabolic scaling. So this is what I do now. Here, parabolic scaling. So the time is scaled by epsilon squared t, and the space is scaled by epsilon x, where epsilon is a small parameter, which means we go to a long time scale tau and to a macroscopic space xi. Okay, and then you can formally do the scaling in your equations, and you get all kind of epsilons, and then you do an expansion and look at leading order terms. And so this is what I do here. Yeah, so the leading order term is p0. And then it needs to be integrated over velocity space, so it's p0 bar. And now the symbol becomes a little bit cumbersome, so I just call it u. Okay, so u now is a leading order term in the parabolic limit scaling of the transport equation. Okay. And then what you get is this. So then the p is replaced by u, and the entire transport thing becomes an anisotropic diffusion term, much in the way I showed you earlier with this nabla colon D of psi, where D is a matrix, a diffusion matrix coming out like this. But the other terms are the same as before. So all these terms here are the same as before, where I just replace U by P. Okay, so that's this one. Now the diffusion matrix, there are certain cases where this is isotropic. In the isotropic case, this becomes D times the identity, okay? So then the matrix is the identity matrix, and we have a scalar factor D, which is then just the diffusion coefficient. And if we have this, here I wrote it again, then the model simplifies a little bit more, where the diffusion term now becomes an isotropic diffusion term. Everything else is the same as we had it before. Okay, so we are not done yet. Oh, but we have okay. But this is a go or grow model. Here I write this. Why? Well, because the U equation, we have a diffusion term. So this is not grow, this is go. Go. So it's diffusing, right? It's spatial spread, which we do not have in the B equation. The B equation has no diffusion, but it has a logistic growth. So this is a growth term. And the same growth term shows up here, but it is dominated by B. It is a growth term from B. So this has a go or go structure. One equation is spatial, the other equation is not spatial, but is reproducing. And so then we have the go or grow type models, which I said have been studied a lot before by all these authors listed here. Okay, one more step. I hope you can do one more step. And this is, here we have the tips U, or the microtubes, and here we have the bulk B. And in the videos, you can essentially count how many microtubes per cell. And you have about 3 or 4 microtubes per cell on average. So which means we have a fixed scaling factor here, which is something like 3.5 or so, or you can write it in the model parameters as well, which relates the tips to the bulk. And if we assume this parameter as well, then we can reduce it to one equation just for the bulk, where we have anisotropic diffusion here, or we can have isotropic diffusion later. But first, for the anisotropic case, then this is the anisotropic model, which I looked at with my collaborators a lot. And if we do consider the isotropic diffusion here, then we get the Swanson model. Yeah, okay, sorry, guys. So the PI model here. Wow, okay, so this is quite a piece of work. So I will summarize this just in a second. Before though, let's just look at this a little bit more. So we now have a standard diffusion term with the diffusivity d half. And then here we have a linear term, we have a quadratic term, we have a logistic term. So you can all put this together in a big Fisher KPP equation or a big logistic growth term, which then becomes this. Yeah, becomes of this form where now mu hat and k hat can be computed from the previous model parameters like this. And this is already a nice result. So this tells us how the growth rate and carrying capacity and diffusivity are related to the tumor microtube dynamics. Right? I showed you earlier that all these parameters I know them from the videos. So I can easily compute k hat right there, bang. So that's pretty cool. Okay. So then we are here. So I walked you through these step A1, A2, A3 to A5, A6 quite fast. But I hope you got the essence of the story, right? So we started here with the microtube model. We found the anisotropic model there, the go-or-grow model there, and the PI model there. So this tells you a wonderful thing. It tells you if I want to use the PI model, the simplest one, well, then I better make sure all these assumptions are satisfied. And if I have reason to believe that maybe assumption A6 is not true, okay, well, then I go back and then I maybe have to use this model here. Or if I think A5 is not satisfied, so maybe then I have to go on this level with the go-or-grow. So you have a very fine structure where you can now scrutinize from the biology which assumptions make sense so that I find the model on the right level for my data. Also, it is a wonderful justification of the earlier models. So I said the earlier models are wrong, but maybe they're not so wrong. Then it just need to be seen in the right context. Okay. Nice. So yeah, maybe I just stop for a sip of water and also invite questions at this stage if somebody wants to ask a question.
Thomas, I think we can keep going, and then around 50 we can have. Oh, so you have further, or this is at the end of your talk?
No, I'm not finished. No.
Oh, yeah. Then please go ahead. Yeah.
Good. Let's see. So let's talk about invasion wave speeds. I know several of you have worked on invasion speeds for reaction diffusion equations. So we have these 6 models, and we put them in a computer, and we look for the invasion speeds. And I'm not telling you which of these lines is which models, but we can clearly see that they have different invasion speeds. So these are 3 of the models here. One has already left the domain, is very fast. So it turns out they all have different invasion speeds. And we thought this is very strange. They should describe the same process. So why do they have different invasion speeds? But then we realized, or actually, I'll show you the speeds here. And then we realized we did scaling, right? We did quasi-steady state assumption. We did parabolic scaling, which messes with the timescales. So all these assumptions mess the timescale up. And so it's not possible to actually compare the invasion speeds directly. Okay, so these are the speeds we have measured in a numerical experiment. Okay. So then let's go back to math and compute these speeds. So for the PI model, for the simplest one, we can just use the Fisher KPP, okay? And we know exactly what the speed is in this case, which is nice. Now, for the go or grow model, Ryan Thiessen has figured out the traveling wave solution. And this is a paper which we just submitted to a journal. And maybe I'll show you this here. Yeah. So the model is here, tip and bulk. Okay. And again, it is a diffusion equation coupled to an ODE. And this is not cooperative. It is a non-cooperative system. So then the general method of Zhao does not work. And we cannot directly compute or estimate the wave speed. So instead, Ryan had to find upper and lower solutions for this model so that we can then estimate the invasion speed. And then we get a formula for the wave speed implicitly as this formula here. And yeah, and here we show the upper solution in pink and the true solution in black. And we see how the solution lies under the upper solution. So, okay. So that's a nice result by Ryan, a fairly mathematical result, not so easy to prove. Okay, so I skipped the wound healing experiments and instead, I show you how this is used for brain tumors. Where is this? Here. Okay. So now we saw these modeling classes, and I just want to show you quickly in the last 5 minutes. Has this ever been used for brain tumor patients, or can we use maybe the full model for brain tumor patients? So where are we standing? And we start with the simplest model by Swanson, the Fisher KPP PI model. And here's a situation where this has been used for a patient. And so you see the black outline is the cancer, as a doctor would have outlined the cancer. And then overlaid in colors from yellow to green to blue is the level lines or level sets for the tumor invasion from the mathematical model. And you see how diffuse it is and how widespread the cancer grows into the brain tissue. And this was really a paradigm change when this came out in 2003, where people for the first time got a feeling for the very diffuse nature of this invasion. And if you only cut out the black thing, you leave so much behind, right? And then the tumor can come back very easily. So Swanson's model has been done for hundreds of patients. And it's used a lot. Maybe it's even more than hundreds of patients. Okay. The next one is the go or grow mechanism. There's a paper by Olivier Sort from 2014, and the simulations look like this, where you have the what is which. So this is the growing compartment, grow. This is the invading compartment, so go or grow. And then they have a necrotic core, which I did not have in my equations. But this is the inner part of the tumor where there's not enough oxygen to grow, so they become necrotic. But it is the major type is go or grow. And this is actually a healthy person and not a patient. So they scanned a healthy person, maybe even Olivier Sort himself, and numerically implanted a cancer. But this was never a real patient. It was just an example. Okay, and then the anisotropic model, this is work I was involved with. We get simulations of this form. Okay, so we looked at 10 patients. Here's patient number 8. And what you see is the black outline is a real cancer. So here, real cancer. And the white outline is our model prediction where the cancer should be. And so the overlap in this picture is very, very good. So the model prediction and the real cancer coincide really, really well. We compare this here with Swanson's PI model. Again, the black is the real cancer, the white is the mathematical cancer. And again, they overlap equally well. So for patient 8, there's actually no difference between our model and Swanson's model, which is nice. The colors here show the anisotropy. So if it's very red, it is very anisotropic. Very blue, it is isotropic. And so you see inside the tumor, the tissue is very isotropic as well. Let's look at a few more of these. So patient 7 in our study. So again, the black outline is a true cancer. The white outline is our predicted cancer. And you can see if you sit close enough to the screen, there's a difference. So Swanson's model predicts a little bit growth here on the right, which is not predicted in our model. So here our model does a little bit better than the Swanson model. And then another patient, patient number 9. So there we see a difference here on the tip of the tumor. The tumor has grown to the upper bits a little bit more than is predicted. And this model does a little bit better, but also is not perfect. Okay. So by using the anisotropic model, we gain a little bit, but this is not the end of the story. This is not maybe a complete answer just yet. Okay. So then this has been done like follows. So here we go again, all our 6 models. And the go or grow model has been done on 1 healthy person. The anisotropic model has been done for 10 cancer patients, and the PI model for hundreds of cancer patients. And that's it. Okay. So none of these models has ever been used yet to model tumor data or to model patient data. Only these 3 have been used. Okay. Whereas this one, of course, is used most. And the anisotropic models for 10 patient and the go or grow model, not even for a sick person. So that's where we are at the moment. Okay. So we have a good understanding now of how these models relate. And we need to focus much more, I think, to make them now patient specific and look at more patient data as they become available. Okay. So then I think, yeah, the timing is great. So I can finish then slowly. First of all, the conclusions. So the tumor microtube-driven glioma model can be reduced to the previous models, which I think is an important observation already. The tumor microtubes open a new target, right? So now you can think about medications to inhibit the microtubes, which is a very interesting study. There are mathematically interesting questions coming from the transport equations and the scaling limits and the traveling waves and all that stuff, which is nice. And yeah, and then they also play a role in the wound healing of cancer, which I did not talk about. So then I put this in brackets here. So thank you very much for your attention, and we can open the floor for questions. Thank you.
Can you hear me?
So now I hear you. Yeah.
Okay. Thanks so much for the great talk. I'm moving away from the speaker.
You have an echo. Yeah, I hear
Yeah.
this.
Okay, so it's a Q&A time. So anyone who has a question, come to me. Yes. And
Or they
then
can type it to
on from the
the.
online, you can unmute and you can ask a question. Yeah, 진수, why don't you come? 야, 밖에서 할까요? 네, 나가겠습니다. Okay, we are in outside.